Okay guys, good morning. I just got back from the grocery outlet store, opened at 8. I figured, well, I'll get there early. No one will be there. Wrong. The place was packed. I had to wait in line for about 15 minutes. Um, they had restocked overnight, so there wasn't empty shelves. So there's a lot of stuff that I couldn't buy. Like sardines were gone, couldn't buy them. There was like one pack of free range steak. Uh, uh, there was like 6 bags of salami. I grabbed 4. I know I'm a hoarder, and they wouldn't let us buy more than 1 dozen eggs. So I wanted to buy 2. I couldn't do it. There were still pistachios, so that was good. But and that was at 8 something in the morning. I can only imagine, by noon or later on this evening. It's a trip. Anyway, this is the problem, right? Okay, so here is the piece of paper, 11 by 8.5, and I'm going to label the squares that we're going to cut off X. And then what we'll do is fold that over and make a box. So the question is, what should the size of the squares be to maximize the volume of the box? Now, we've done this problem before last semester. You might remember when we were learning derivatives. So each side of the box, notice you take away these 2 x's, so you're left with 8.5 minus 2x, and you take away these 2 x's, you're left with 11 minus 2x. So this dimension of the box, we multiply length times width times height, we get the volume. So here's our volume equation. Now notice this is a cubic equation, right? And notice it's a positive cubic equation, and if we put this equal to 0, we get the x-intercepts, which would be 8.5 divided by 2 and 11 divided by 2. So here's a graph. We know it's going to go up on the right and down on the left, and so since we have the x-intercepts. Okay, well the only way this will work is if we have a positive volume. Notice based on the graph, we're only going to get a positive volume when we're between 0 and 4.25. And you might say, well wait, what about after 5.5? You are right. But look how unrealistic that is. If we're greater than 5.5, this is going to become 0 or less. So the realistic model of the problem is going to give us potential solutions between 0 and 4.25, and that is the maximum volume, that hump. Now, you can make a table. So where's the calculator? I just had it. Give me a second. I just had this thing. Calculator. Oh. Staring me right in the face. So for instance, I just went to the y equals. It's got to be on. So I just went to the y equals, and so you can see the equation there. And then I went to the table set. And you can start it at 0 and go by 0.2. And then notice that the maximum value is somewhere between 1.4 and 1.8. And so we could do the same thing that we learned last semester. We could just say, okay, so 1.4, let's go up now by 0.1. Scroll that down. Oh, it looks right around 1.6. So somewhere around 1.6. And then you can do the same thing, set the table, start at 1.6, and then maybe go by 0.01. And look at that, somewhere around 1.58, 1.59. So that's one way you could do it. But we learned how to take the derivative last year. Or at least we attempted to learn. So if we want to find the value of these humps, remember the derivative is the slope of the tangent line. Right? And so when the tangent line slope is 0, we're going to get these locations. So take the derivative, remember the power rule, 3 times 4, subtract 1 from the exponent. 2 times 39, subtract 1 from the exponent, and then this is a linear term, so the slope 93.5. You could think, 1 is the exponent times 93.5, subtract 1 from the exponent, you get x to the 0 power, which is 1. So put this equal to 0, quadratic formula, and these are the solutions. And so notice this one we throw out because that one is right here. And that's the volume we would get. So that's our maximum volume, which is in the interval that we've already stated. Okay, that's how you do that problem. I'll send y'all another problem of the day a little later and begin to start dialoguing with y'all on the Gmail and Google Classroom.